Assalamualaikum and good day. I'm to Dr. Noazala and friends. We are from Group 2 and today we are going to present the lab report for Experiment 1, which is Bernoulli principle. So these are our group members, Mak Irfan, Yusuf and me, Alana Suha. Next is introduction. In fluids without any energy exchange, energy expressed as pressure, velocity and elevation because of heat transfer, shower or viscous dissipation. Daniel Bernoulli was the first to invent this relationship between three types of energy using the conservation of energy concept. So he made assumptions regarding a flow streamline, which are steady flow, incompressible fluid and also absence of fluid friction losses. So this experiment will investigate the validity of Bernoulli's equation. Next is objective. The first objective is to compare the measured and calculated fluid flow velocities in the venturi nozzle at different points. Second, to investigate the static, total and the dynamic heat distribution along the venturi nozzle. Third, to determine the flow coefficient at different fluid flow rates. Next is theory. So as you can see, the first equation is the equation for the constant heat. This is the general equation for Bernoulli, and then we consider the friction losses and conversion of P1 and P2 into static heads. Then equation 2 will be formed. As you can see at the picture, this is a venturimeter. Venturimeter is a flow meter that works on the principle of Bernoulli's equation. We move to the theory part. The venturimeter will be in closed system. Hence, the mass flow rate for point 1 and 2 will become constant. We will simplify the variable of the mass flow rate and we will end up getting constant volumetric flow rate for both points. For equation 3, this is the equation that we will use to find the reference velocity. A1 is the area at point 1 while A1 is taken from the table. The volumetric flow rate will be used in equation 4 to find the initial values for the theoretical velocities. For the equation 5, h total minus with the h of static head, we will get the value of dynamic water column head. Then from the value of h dynamic, we will proceed to find the experimental velocity in the equation 6. In order to determine the flow coefficient, which is Kv, we need to know which variable correlate with the value of flow coefficient. In equation 7, it is shown that volumetric flow rate has relation with it. To proceed with the calculation, we need to rearrange the equation so that Kv will be the only variable at the left side. Then we will get equation 8 to find the flow coefficient.
So this is our experimental setup. So this is our methodology. So for the first step, main switch and pump were switched on. Second step, the control outlet valve was opened slowly until maximum level to remove air in the pipe system. Third step, the black cap valve on top of the manometer was slowly opened to release all bubble in the system. Then the black valve was closed. Fourth step, the control valve and the pump was closed. Fifth step, the white valve was slowly opened until 80 to 100 millimeters. Sixth step, the pump was switched on again. Next step, the control outlet valve was opened slowly until level of manometer in P1 reached maximum and P3 at minimum level. So the eighth step, the reading at manometer for P static and P total for point P1, P2, P3, P4, P5 and P6 were taken. Simultaneously, the volume of water collected at the tank for each point with the time was recorded. So step number 9, the outlet valve was adjusted by reducing the flow to determine another reading. And lastly, step 7 and step 9 were repeated.
So this is the result that we get after the experiment. For the discussion, first of all, we need to calculate the fluid flow velocity in the venturi nozzle at the different points. As we know, we want to find a theoretical velocity, so we need to use the formula W equal to V A I. W is the velocity, V equal to flow rate, and A equal to the area. From the calculation, we can see that the point 3 has the narrowest area, which has the highest velocity. So this is proof that the higher area, so the lower the velocity. After that, we need to find the experimental velocity. So we need to using the formula, which is W equal to square root 2G high dynamic. So from the equation, we know that the higher the dynamic, so the higher the velocity. So after we get the theoretical and the experimental velocity, so we can find the percentage error for this experiment. So the table showed that the percentage error of P1, P2, and P3 quite small compared to the P4, P5, and P6. This is show that the value of the theoretical and experiment are very close. And the higher the percentage error is 64.43, and the smallest percentage error is 0.25. Next, calculate and discuss the static, total, and dynamic head distribution along the venturi nozzle. From the chart, we can see that the H total decrease along the venturi, while the H static decrease until 56 millimeter, then increase again. But the trend of height dynamic opposite to the height static, which is the height dynamic increase until the length of section at 56 millimeter, and then decrease after 56 millimeter. Lastly, calculate the flow coefficient at the different fluid flow rate. So we need to use the formula Kv equal to V over square root G delta H. So V represented by the volumetric rate, and change of height we can find from uh, height static at point 1 minus height static at point 3. So as the result, we can see that the flow coefficient decrease when the flow rate decrease.
So this is our safety procedure. First, make sure no water leaking from the bottom of the tank. Next, make sure no water bubble in the manometer. And lastly, ensure all valves are closed and any pump or electrical equipment are turned off after completing the experiment.
In conclusion, this experiment meets the Bernoulli principle. From the theory, we know that if the fluid pressure higher, so the velocity will lower. From the experiment, can be proved when the fluid pressure increase eventually, so its velocity will decrease.
For reference, this is all the references that we use in this experiment. That's all from us. Thank you.